Here in our first warm-up, we're trying to think of how to do a derivative when we don't have a base of e. We know that the derivative of natural log is what? Natural log of x is 1 over x. Okay? How do you think we might handle a log with a different base?
Change it to ln base.
Can I change to ln x over ln2 or ln?
Yeah, we're going to change the base, change this so that it's no longer ln base 2, but we're going to take the derivative of ln of x over the ln of 2. Now, we may not know what ln of 2 is off the top of our heads, but we do know that it's a constant. Okay? So, since it is a constant, I can simply take that constant out and take the derivative of just ln of x. Okay? So, this is now going to be 1 over the ln of 2 times that 1 over x. So it's going to be 1 over x times the ln of 2. All right? So that's how we can handle logs with a different base. You can change the base so that it is e. It's something you know how to do. All right? And then take the logarithm that way, okay? Now, can someone tell me, can you generalize this? If I had a log base a of x, it's ln of x over ln of a, so what would the derivative be? Okay. I think I heard it in there somewhere. Okay. You end up taking ln of whatever the base is, right? And it's 1 over that. Okay? So it's 1 over ln of a, but it's times the derivative of ln of x. So it's times a 1 over x. So it's 1 over x times the ln of a. All right? So that's a little rule that you could remember that might make your life a little easier later. Okay? But you also see where it came from, and you could rederive it pretty easily if you had to. Okay? All right, so then number 2. How would I solve this equation? 3 to the x is 1 over 81. Log what? Do a log of both sides. Now what base would I use for my log? Yeah, let's use a log base 3 of 3 to the x, because that will just give us x. Right? And we can do a log base 3 on this side as well. Now what is 1 over 81? Can we rewrite that? It's 1 over 9 squared. Huh?
3 to the 4th.
3 to the 4th. It's 1 over 3 to the 4th, right? So that's 1 over 3 to the 4th, which means that it's also 3 to the negative 4th. So what's the log base 3 of 3 to the negative 4th? Negative 4. Okay? So there is our solution for x. Okay? Make sense? All right. So now let's look at the definition of an exponential function to base a. All right, now a couple of things here. Instead of e to a power, we're doing a to a power. Okay? And you'll notice here, it says if a is a positive real number and a does not equal 1, and x is any real number, then the exponential function to the base a is denoted by a to the x and is defined by this equation right here. Okay? A to the x equals e to the ln of a times x. E to the ln of a times x. Now, how are these equal? Well, let's take a quick look at this, okay? First of all, in the exponent on the right-hand side, I have x times the natural log. Well, you guys know if I'm multiplying the natural log by something, I can take that thing and make it the exponent inside. So I could rewrite e to the ln of a times x as e to the ln of a to the x. Okay? Now, the reason why that's significant is because, as we saw before, exponentials and natural logs, natural exponentials and natural logs are inverses of each other. Therefore, this simply equals a to the x. Okay? So that's kind of the intermediate step in there as to how we get this definition, okay, of what a to the x is. Now, seeing this is important as we look to take derivatives, okay? Now, there are a couple of other properties I want to make sure that we remember. Remember the properties: if you raise something to 0 power, you get 1. If you're multiplying things with the same base, you can add the exponents, so it's x plus y. If you're dividing things with the same base, then you would subtract the exponents and keep the base the same. And of course, if you're raising something to a power to another power, then you can simply multiply those powers together. So a to the x times y in this case. All right? So those really at this point should be kind of no-brainers for us. We should know those pretty well. But let's actually take a look at some applications where we're going to need to use this kind of a thing, okay? So first of all, we have the radioactive half-life model, okay? The half-life of carbon-14 is about 5,730 years. If 1 gram of carbon-14 is present in a sample, how much will be present in 10,000 years? Okay? So the starting amount, if you remember our formula, the amount after t years is equal to the starting amount, a sub 0, times 1/2 to the t divided by k power. And k is the half-life. All right? Now, the reason why we have to do t divided by k, if you remember back from pre-calculus, is our rate is minus 50%. How often? Every k years. Every half-life. Okay? Every 5,730 years. All right? T was in years. Okay? So if I do t divided by k, that gives me the number of, and I don't know if this is even technically a word, half-lives. All right? Half-lives? Half-lives? I think it's half-lives. Okay? So we're basically just converting our unit of time into half-lives instead of years. All right? So in this case here it says how much will be present after 10,000 years? So we're trying to find A of 10,000. Okay? The starting amount is 1 gram. And we're going to multiply a half by T, which is 10,000, divided by K, 5,730. So that is 1/2 to the 1.7452 power. Okay? So now all we have to do is raise a half to that power, 0.5 to the 1.7452 power, and we get 0.29829, and this is in grams. Okay? So that's just a little reminder as to how we do half-life. Does anyone have a question about what we've done here?
Yeah, I have the question about the T over K.
Yeah.
Yeah,
It's K over T. Or no, I'm sorry, T over K, yeah.
yeah, I just don't know how this came from.
Well, again, the whole reason why we do that is this is every K years. Okay? That right there, 5730 is K. Alright? Our rate and our exponent in this is an exponential growth problem. Okay? Our rate and our unit of time for our exponential growth have to be in the same units.
Okay, I got it, yeah.
Yeah.
So it's like every 5,730 years, the carbon-14 will be half-life?
Yes. Yeah, after and that's why we know the answer here should be less than a half. Because if we started with 1, after 5,700 years, it would be down to a half. We went 10,000 years, so it should be approaching a quarter, you know. All right. Yes.
So where's the is there any calculus involved?
No, this question has no calculus in it at all. All right, you're not missing anything. This is just a quick review for us of this idea. Okay. Now we have a logarithmic function of a base of A. Okay, a base A, and here you have what we would call the change of base formula, okay? Except here specifically, they are changing the formula or changing the base to E every time. And the whole reason behind that is because we know how to take derivatives and integrals of E, okay? So we have the log base A of x is 1 over ln of A times ln of x, or using the change of base formula in the form we're a little more used to seeing it in, ln of x over ln of A.
Does it flip-flop? Can you do the same? Like if you have the ln x and want to go to the log, does it do the same thing?
Wait, if I have ln of x...
Like let's say you go the opposite direction, so how do you do the change of base from ln to log?
Oh, if you have ln of x, this applies no matter what A is. Okay, and I can change it to any base I want. Here I'm changing to base E.
Okay.
I could use the same property for the common log of x over log of E, if I want.
Okay.
Or I could do the log base 7 of x and the log base 7 of E, as long as they're the same. For our purposes, because we're doing the calculus, we're going to be changing stuff to natural log whenever we can. Okay? So again, here we have a couple of properties of our logarithms. We've used those quite a bit already. But take a quick look, remind ourselves of the properties of inverse functions. Because remember that exponentials and logarithms are inverses of each other as long as the bases are the same. Okay? So y equals a to the x if and only if x is the log base a of y. A to the log base a of x equals x. Alright? An exponential and a log are inverses so long as the bases are the same. And there you see number 3, the log base a of a to the x is just x. Again, you have those inverse properties. Okay? So, a little bit more review here. How would we solve for x in this case? I'm sorry, what? Wait, are you saying, did you say 3 to the x over 2 squared? Is that what you said?
No.
Oh, what did you say?
Maybe that will work.
Probably
Yeah,
that
that
will
will
work.
work. That looks.
Well, it's not any better, it's just, it's possible, but...
Log 354 equal to x over 2.
Okay, if I take the log base 3 of both sides, then yeah, my inverse property here, that gives me x over 2 equals the log base 3 of 54. Okay? Then I can multiply both sides by 2, and I have x equals 2 times the log base 3 of 54. Now, some of you have calculators that are able to do different bases. A newer TI-84 has it. An older TI-84 has it, but it's buried in a menu somewhere. I can't remember. All right? And the 83s, you're on your own, okay? But the nice thing is the change of base formula is really easy. So if I wanted to actually evaluate this, I would simply do 54, and I would do the natural log of that, okay? So I'm rewriting this as 2 times ln of 54 divided by ln of 3, okay? So ln of 54 is 3.988984, and so on. If I do the natural log of 3, I get 1.09861128 or 1228 and so on. I'll just do 123 to round. Okay? So, again, this is just arithmetic here. So I'll divide 2 by that and multiply by the 3.988984, and I should get 1.815. Since we have 3 decimals, I'll stop there. Okay? All right. Not too bad. Should actually be kind of a nice, relaxing, much easier lesson than some of the ones we've had recently. Okay? Yes?
Isn't that basically 4 divided by 1? Like it's 3.98 divided by 1.09. So shouldn't that be like 3 times 2? Shouldn't it be closer to like 7?
Yeah, let me see here. 3.988984 divided by 1.098612 up times 2.
Yeah. Okay.
Yeah. There's something up with the how I was punching it into this calculator. Alright. 7.262 if you round to 3 decimals. That's better. Thank you. Okay? All right, any other questions, comments, anything? All right, how about this one?
Yeah, x equals 2 to the negative 4.
Oh, okay. If you just remember the base becomes the base of the exponential. What the log equals is the exponent, and the argument is what that will equal. So x equals 2 to the negative 4th, or x equals 1/16. Okay? Alright, so now we get to actually do some calculus. Okay? We want to find derivatives for bases other than e. Okay? Derivatives for bases other than e. Alright, so here we want to do the derivative of a to the x. Alright, now you'll notice here number 3. Number 3 we actually already derived earlier. Okay? If you have the derivative of a log base a of x, it's going to be 1 over ln of a times x. And then, of course, here, this is just the same thing as number 3 with the chain rule. If it's a log base a of something other than just an x, it's going to be 1 over ln of a times whatever that is. But then you have to multiply the whole thing by the derivative of that u. Okay? And here you kind of see that u prime over u idea. You remember that? The u prime over u?
Yeah.
Okay? It's just we have the 1 over ln of a in changing our base. Okay? Now, these two rules we haven't looked at yet. Okay? So I want to actually go back to that definition of what a to the x actually is. What did we say on the earlier that a to the x actually equals?
It's e to the ln of a to the x power to the x power.
E to the ln of x, or I'm sorry, ln of a times x, right? Now, once you rewrite it like this, you guys know how to do the derivative of that. That's simply chain rule. Okay? So if I'm taking the derivative with respect to x of this, the derivative of e to a power is e to that power. So it's e to the ln of a times x.
X 1 over x
It's just 1 over, it's just times ln of a. This is linear up in the numerator, right? This is a linear.
Oh, because of the con.
Because x is to the first. Yeah, ln of a is a constant. Alright? So the derivative of something linear is just whatever that constant is. So this is going to be times ln of a. Okay? Now, what is e to the ln of a times x? That's a to the x, okay? So this is ln of a times a to the x. Alright, so the derivative of e to a power is just e to a power. The derivative of anything else to the power is whatever it is to the power, but times ln of the base. Okay? So whatever this base is, you're simply, it's just like e to the x, where you write it down identical to how it was, but you also have to multiply by ln of the base. Okay? So, and then of course number 2 is the same thing, just now we also have the chain rule on top of it. Okay? So let's actually try a couple of these just for some practice. Okay? part A, the base is 2. So if I'm finding dy dx, I'm going to write it down identical to how it is, so 2 to the x, but then I multiply it by ln of the base, 2. So it's going to be ln of 2 times 2 to the x. Alright? For part B, notice this is 2 to the u power now. It's not just 2 to the x. Alright, so here, dy dx, I write it down identical to how it is, 2 to the 3x. I multiply by ln of the base, but then I also have to multiply by 3, the derivative du dx. Okay? So yeah, u here was 3x. So du dx is just 3. So that's what I'm plugging in right here. Okay? Be careful simplifying. This one, there's really not much to simplify. You could do 3 times ln of 2 times 2 to the 3x. If you really want to, you could bring that 3 on the inside as an exponent and make it ln of 2 cubed, or 8, times 2 to the 3x. It's totally up to you. All right?
Wait, but you're saying 3 times ln 2 times 2 to the x is equal to that?
Yes, because you could bring the 3 in as an exponent, remember?
Oh.
Bring it into the natural log as an exponent. Okay? All right, and then finally, the log base 10 of cosine of x. Okay? Let's write down a couple of things here. The base A equals 10, and u here equals, well, u is cosine, but du dx is negative sine x. Yeah, du dx is negative sine x. So, dy dx is going to be, remember the like u prime over u idea? It's the same thing here. We're going to have du dx over u times ln of a. Okay, that's our formula. Written a little bit different than the previous slide, but that's the idea. So we have a negative sine x over ln of 10 times u times cosine.
Why is ln like a at the bottom?
Because you have to change base, all right? What you're doing here, what you're really doing here is you're doing ln of cosine of x over ln of 10. Okay? So you're going to do the derivative of ln of cosine, which is u prime over u, so negative sine over cosine. But you have this 1 over ln of 10 as a constant that you got to multiply it by as well. Okay? Yeah?
Could you simplify that to negative tangent over ln of 10?
Yeah, sure you could. Negative tangent x over ln of 10. Do you have to? No. Would it be helpful sometimes? Sure. Might it be a choice on the multiple choice where they don't give you negative sine over ln of 10 times cosine, but they do give you negative tangent over ln of 10? Sure, that could happen. All right? You're expected to know all those things, right? So, okay? All right. So that is it for that lesson there. Again, not a ton of brand new stuff, but having to handle this, there's just that extra little part that you have to do in order to handle the different base. Okay?